So let's imagine we've got a cross product of A cross B equals some vector C. And C written out in component form would be CXX hat plus CYY hat plus CZZ hat. Let's see if we can't figure out what are these components by writing our vectors A and B in their component form. So A is AXX hat plus AYY hat plus AZZ hat. And we will cross that into B, and B is BXX hat plus BYY hat plus BZZ hat. With the distributive property, the cross product of these sums we can then separate into cross products of each individual term. So just like we were multiplying two numbers that were the sum of 3, we could just take the first times the first times the second, first times the third, etc., etc. So that's what we're going to do. We're going to cross these and see what we get. So first times first is x hat, so it'll be ax times bx times x hat cross x hat. But we know x hat cross x hat is 0. And then we'll have this term cross this term. So we'll have ax, bx, x hat cross y hat. But we know that x hat cross y hat, x, y, z, is z hat. And then we'll have this term times this term, so plus ax, b, z, x hat cross z hat. But x hat cross z hat is negative y hat. So I'm going to replace this with a minus y hat. Very good. So that's the first term crossed all of those. Let's do the second term. We have ay times bx, so ay, bx, and then y hat cross x hat. Y hat cross x hat, that's going backwards, so that is negative z hat. And then we'll have y hat cross y hat, but that's 0. And then we'll have y hat cross z hat. So this will be plus a, y, b, z, and y hat cross z hat is x hat. There we go. Okay, so that's the second term crossed all of those. Now let's do the third term. So we have azbx, so azbx, and z hat cross x hat, that's y hat. So remember, x, y, z, x, y, z, so z, x, y, so that's going to be a positive y hat. So plus that term. Then we'll have azby, azby, and z hat cross y hat. Well, that's going backwards, so that's going to give us a negative x hat. And then z hat cross z hat, and that is 0. So there we go. That is the cross product of the whole thing. Those are all the terms. Now, let's bring all the x hat terms together, the y hat terms together, and the z hat terms together. And what do we get? So this is, where are the x hat terms? We've got an aybz, aybz, minus azby, minus azby, and this is all times x hat. Now, just for the sake of making things a little bit easier to remember, I'm going to write this x hat in the front over here. So x hat. Okay? And let's do the same with the y hat. We'll see why in just a second. Y hat. So where are the y hat terms? We've got here azbx, and then minus axbz. And then let's do the same with the z hat term, plus z hat times, and where are the z hat terms? We've got one here, whoops, sorry. This was this term, x hat cross y hat. This should be axby, sorry, miswrote that, so that's by. So we've got axby, and then minus aybx. And there we go. So notice, we've got the x hat term, the y hat term, the z hat term. So this is going to be cx. This is going to be cy. And this is going to be cz. Now, that looks very, very complicated, but let's see if we can't do anything to help us remember this. Well, let's notice here. So if we look at the unit vector and then the component of A and the component of B, we have x, y, z. And then minus zy. Here we have y, zx, and then minus xz. And here we have z, xy, minus yx. Well, notice we've got that same rotating cyclical pattern. X, Y, Z, Y, Z, X, Z, X, Y. X, Y, Z, Y, Z, X, Z, X, Y. For all of the positive terms. But then don't forget we've got to subtract the negative terms. Okay, there we go. That is the cross product in terms of the components of the vectors. So we've got two ways of determining the cross product of a vector. We know that A cross B is equal to, in magnitude, AB sine phi, and the direction we get by the right-hand rule. So that's one way that we can determine a cross product. And then we can determine a cross product if we know the components of the vectors A and B. We can combine them and find the cross product in this way. Okay, excellent. This actually turns out to be a very interesting form that we can write in terms of the determinant of a matrix. Let's take a look at that. If we have a matrix with components on the top row, x hat, y hat, z hat, so this is kind of a funny matrix. It's got actual unit vectors for part of the elements and then numbers for the other elements. Across the second row, we have the components of the A vector, ax, ay, az. And across the bottom row, we have the components of the second vector, bx, by, bz. For this matrix, if we were to take the determinant of this matrix, it turns out that we get exactly this form. In other words, remember, how do you take a determinant of a matrix? If you don't know, don't worry about it, but this is how you do it. You take the top first element on the left, x hat, and then multiply it by the determinant of the, crossing these out, the lower 2 by 2 matrix. Takes this determinant, which is aybz minus azbx. Then you take, you subtract y, the y hat, times the determinant of what's left, these terms here. So minus y hat times axbz minus azbx. And that gives us this, with the minus sign. And then add the z hat times the determinant of what's left, which is this part. So z hat times axby minus aybx, and that gives us that term. So, turns out, this is exactly the form of taking the determinant of this 3 by 3 matrix. Okay, let's actually try this. Let's stick some numbers in here. We'll take a couple sample vectors and find the cross product. So let's imagine we have a vector A, which is 2x hat plus y hat minus 3z hat, and a vector B, which is x hat minus y hat plus 2z hat. And let's calculate what is A cross B. And we'll use our result right here. So this is going to be equal to x hat times AY, which is 1, times BZ, which is 2, minus AZ, which is negative 3, times BY, which is negative 1, plus y hat times AZ, which is negative 3, times bx, which is 1, and then minus ax, which is 2, times bz, which is 2. And then plus z hat times ax, which is 2, times by, which is negative 1, and then minus ay, which is 1, times bx, which is 1. Okay, there we go. Now, what do we get? Well, we get 1 times 2 is 2, minus negative 3 times negative 1 is positive 3, so 2 minus 3. We get negative 3 times 1 is negative 3, minus 2 times 2 is 4, and 2 times negative 1, that's negative 2, minus 1. So what do we end up with? We end up with 2 minus 3, that's negative 1, or negative x hat. Negative 3 minus 4, that's negative 7, so minus 7 y hat. And then negative 2 minus 1 is negative 3, so minus 3z hat. There we go. There is our cross product. Let me just check, make sure I didn't make any mistakes. Negative 1, yes, very good. You didn't make any mistakes. So there's the cross product, A cross B. But one more thing I'd like to notice is, let's say that this is our vector C. Let's call that C. Let's figure out what is A dot C. What is A dot C? Well, that's going to be A 2x hat plus y hat minus 3z hat dotted into C, which is negative x hat minus 7y hat minus 3z hat. Okay, now how do we take the dot product? Remember, the dot product of two vectors is the product of the x components plus the product of the y components plus the product of the z components. So the dot product in this case will be the x components, 2 times negative 1, that's negative 2, 1 times negative 7, and then negative 3 times negative 3, so that's plus 9. So we get negative 2 minus 7, that's negative 9, plus 9, it's 0. 0. So A dot C is 0. Does that make sense? Well, yes it does, because what did we say? The cross product of two vectors should be perpendicular to both of the vectors that we're taking the cross product with. So C should be perpendicular to both A and B. And what's the dot product of two vectors that are perpendicular? Remember, A dot C will be AC cos theta. And if A and C are perpendicular, theta is 90 degrees, cos of 90 is 0, we should get 0. And that is exactly what we've done. Taking the dot product, we get 0, which shows, since neither one of these is 0, it shows they must be perpendicular to each other. All right, great. Let's try B dot C. What is B dot C? Well, we have B is x hat minus y hat plus 2z hat. And we're going to dot that into C again, negative x hat minus 7y hat minus 3z hat. And what do we get? Again, x components, 1 times negative 1, that's negative 1. Y components, negative 1 times negative 7, that's positive 7. And 2 times negative 3, that's negative 6. Negative 6. And what do we get? Negative 1 plus 7 is 6, minus 6, 0. Again, we have shown then that these two vectors are perpendicular. So great, when we take the cross product, we get a vector that is both perpendicular to A and perpendicular to B. Very, very good.